Hello, everyone. Thank you for joining again another live event on embedded software and systems development. Today, it's HIL test automation for safety critical systems. My name is Annette Kempf. I'm the CEO of Eclipseina, training provider, which is also working in charging communication. So we are, this branch of training providing is with trainings on site at our new location in a historic brewery building, as well as e-learning, live events, and many, many more things. Today, I have the guest, Thomas Schütz from Protos Software GmbH from Munich, and he will share some of his deep knowledge on how to test efficiently embedded systems with us. I'm really, really happy to have him here again. And what I also want to mention is that Thomas Schütz is, in addition to this, the trainer on our software architecture training for embedded systems, which he's doing on-site at our location, but he also performed the trainings at different customer locations in the past. So now let's welcome Thomas Schütz for this technical talk. Thank you for being here, Thomas, and I will hand over to you now.
Yeah, thank you, Annette, for the opportunity to speak here. Yeah, the topic, as you mentioned before, is HIL test automation for safety critical systems. And I dig right into the meat here. So why are we doing what we're doing with regarding to testing of safety critical systems? So let's imagine a real world problem, like you have a traffic light in one direction and at a crossing, at a car crossing, and in the other direction you also have a traffic light. And imagine both traffic lights are green. Yeah, you can imagine what will happen. That's exactly what we want to avoid. And how can we avoid this behavior, this erroneous behavior in complex software and systems? So the systems get more and more complex. Doesn't matter whether it's the hardware or the software, but usually it's the software that gets much more complex because it has much more degrees of freedom. So if you want to change your hardware, that's really hard to do. It's very expensive. If you change your software, it's cheaper. You have much more dimensions you can change, but it also gets much more complex. And that's a real problem, especially for safety critical systems, but not only for safety critical systems. We want all our systems we deliver to be robust. But let's focus on safety critical systems for now. The first question is, on which levels can I test software for safety, or in general systems for safety? Let's have a look at a typical embedded system. We have the system, for example, with a motor, a pump, a hydraulic system. This could be a lubrication pump. This could be a blood pump for medical devices. This could be a water pump in a house. Whatever it is, you can imagine that many of those systems might be safety critical, especially in the field of medical systems, but also a lubrication pump can be very safety critical. If, for example, it's attached to a crane or to an oil rig, if it doesn't work, the crane doesn't work and it might fail with consequences. So inside the system, you have the control unit, the electronic control unit, with the power electronics, with sensors, with actuators, and so on. Inside the ECU, you have usually a microcontroller or several microcontrollers with the application software and with the drivers, or in AUTOSAR, for example, in automotive, the microcontroller abstraction layer. So let's talk about drivers now. And on top of that, you have the software stack with your software units. Now, on which levels can I test those systems? Let's start with the smallest unit, with a unit in your programming language. This would be a C module or a class in your system. The test for such a unit would be a unit test. One level up, you have a software integration test. you bring several units together, and you still can use a unit test framework to execute this kind of test. It's a pure software test, and you cannot test everything with pure software unit test. So for example, unit 1 and 3 here, they might be asynchronous, concurrent, state-based, or controller-based, loopback controllers, and that's already really hard to test only with a unit test. You need a different approach, something like software in the loop or something like that. One level up, if you want to take the drivers into consideration, you cannot get around using a hardware approach, because even if you could test those software units here with a software test, hardware drivers, for example, PWM driver or something like that, that's really, really hard to test, or even impossible to test with a software approach, because it uses partially hardware. So the next level would be the hardware-software integration test. Basically, you take the microcontroller or a group of microcontrollers as your system under test, and you test at the pins of the microcontroller. That's basically the smallest possible hardware in the loop test, and that's also the level we're focusing on now. One level up, you already have a bigger hardware in the loop setup with the control unit, with the complete electronic control unit. So in this case, big hardware in the loop test, you would already need some power electronics to test your power electronics in your hardware. You need to emulate sensors, real-world sensors, for example, a temperature sensor with a climate chamber or something like that. That's already really hard to do, and especially very expensive and very slow. But it's a good test. Please don't take it wrong. It's a good test. The next level up is the final system test, where you actually use the real-world system to run tests. For example, you get into a car and drive around the block or through the desert Nevada. But that's really hard to do, even harder than a hardware-in-the-loop test, and it's very expensive. After every software change, you do not want to drive through the desert with your car. So now let's have a look at on which level can I test for safety. The first two levels are pure software unit test levels. It's very good to achieve a high code coverage, but it's not very good to test complete software functionality, because you're always missing something. But it's a very good test. It's easy to do for hardware, for safety critical systems, but it's by far not enough. So the highest levels is hardware in the loop test, a big hardware in the loop test, or a system test. It's a very high effort to deeply test the software functionality. And the hardware that's attached to your system is really problematic with respect to failure injection. So if you have a motor attached to your system, you need to break the motor to test what your system does in case of a motor failure. Or in case of a climate chamber, for example, for a temperature sensor, you need a climate chamber to test whether your temperature sensor works or your software for the temperature sensor works. That's why we're focusing mostly on hardware and software integration tests. That's smallest possible HIL test, and it's very good to test the complete software functionality on your microcontroller as a black box, including all the error paths. So for example, if you want to test the temperature sensor, you do not need a climate chamber. You just attach the analog value to your microcontroller, and you simulate the temperature sensor by generating analog signals according to the temperature that is expected. By doing that, you can test all the error paths for your temperature sensor and for your complete application, or at least most of them. You never get 100%, but you get much more than with a unit test or with a big system test. So that's the basic idea here. Now, what do we need for different kinds of systems on different levels? We need always a test harness. So a test harness usually has the test cases on top. But you also need to satisfy all the open interfaces on the bottom. So for example, if you call a function, you will soon see that the function also calls other functions in your ECU on software level, on hardware level. And in order to isolate test your system or your component under test, can also be a software unit, you need to satisfy all the interfaces, not only the interfaces you want to test, but also the interfaces under the hood. So you take the component out and you see that you have 500 includes in your component and thousands or hundreds of calls to other functions and other components or other classes. And you need to satisfy them all to isolate your component in order to test it. And this together is called a test harness. Now, you can have unit tests, for example. Unit tests are synchronous, and they usually, so the test cases are synchronous. So you call a function and you wait for the return value. And that's a synchronous test. And at the other end, you need to stop and mock functionality that's called from your system under test, from your component under test, or from your software unit. So that's all synchronous. That's relatively easy to do. Most unit test frameworks have some mechanism for stubbing and mocking. So that's solved the problem. There are many good frameworks out there, and it's very useful to really dig into the details of your implementation. So that's very important. But as soon as you get to the integration and system test level, you have a completely different situation. Suddenly you have asynchronous system, concurrent systems, you have threads, you have things that work in parallel. While the CAN bus is working, you need to check the temperature value and control your motor. Those would already be three things that are completely asynchronous and concurrent from each other, and you need to test them. And also at the stubbing mocking level, you do not get away with stubs and mocks. You need to satisfy the interface by doing closed and open loop simulations. So for example, an open loop simulation would be to give to if the system under test is a microcontroller, you need to stimulate for the temperature sensor an analog value. So you need a hardware analog value. So 3.3 or 5 volt. A real hardware signal. That would be an open loop simulation, because you do not have a control loop. You just set the value and that's it. But for things like a motor control, you have a closed loop controller. For example, you speed up the system and your motor follows. So you need a simulation instead of the real motor. You need a closed loop simulation, plant simulation, to simulate the motor, or also a temperature if it's a temperature controller or any other system. And you need to simulate the behavior of the environment, in this case with a closed loop simulation. That's very important, because if you just play back a recorded signals, for example, for a motor, your controller will not work. It will immediately go to an infinite level up, or it will go to zero. So because the motor needs to follow in order for the closed loop to work. And that makes asynchronous tests much more complex, or at least more complex. So that's what you need. And you need more than test cases. So the test case actually in asynchronous test systems is not the most complex thing. It's usually the environment simulation, the simulation of all your interfaces. So now we know what we need for our testing for embedded system. So how do I simulate the environment for unit tests? So in a unit test, usually you simulate the interface directly on the level of a programming language by directly calling functions. So it's synchronous, sequential, not concurrent, no states or history, or at least not much. You usually create stub functions or objects that emulate the behavior of the environment. So for example, if you expect something to deliver the value true, you just return the value true. So stubbing is just to satisfy the interface. Mocking usually implements a very, very simple implementation in order to be able to influence the reaction of your test harness. So the simulated object is there to mimic the behavior of the environment in a very simple way. Now, how do I simulate the environment for hardware-software integration tests or for system tests? So asynchronous, it's concurrent, it has states, it has history. Of course, your ECU has a history and it has states, because if not, it would not work. So it's mostly those kind of tests are mostly implemented as in-the-loop tests. So model in the loop, software in the loop, processor in the loop, hardware in the loop, and so on. So that's usually a category of tests that uses environment simulations, not mocking or stubbing. You have those open loop simulations, as I explained before. They do not have a feedback loop. So for example, predefined sensor values, if you want to test all the equivalency classes for your error shutdown for temperature sensor, you just say, okay, now the temperature is minus 40 degrees, minus 39, minus 1, 0, 1, 39, 40 degrees plus, something like that. So those would be the equivalency classes of your temperature test. You just can write them and that's it. A closed loop simulation is, as I mentioned before, for example, for a motor simulation where the motor really follows the controller. Also a temperature simulation, a range simulation, things like that. So if something is controlled by a closed loop controller, usually you need a closed loop simulation to really test your system. Sometimes you get away with something else, but with an open loop simulation, but that's another story. Most interfaces can be simulated open loop. Usually the core of your application needs to be simulated closed loop. If you have a motor controller, you need a closed loop motor simulation. Now, another aspect is the development process. Where in the development process do I test what? That brings another dimension into play. So let's assume you start on an evaluation board to define your software, to develop your software. First, you start to develop your drivers or to configure your drivers. Then you have some hardware-related software components like a motor controller, a CAN bus, a LIN bus. So all those hardware-related protocols and so on. On top, you have your software components, usually the application logic, some access, maybe a human-machine interface or whatever it is in your embedded system. And you integrate everything and you get your application by integrating everything. Eventually, you might move to your real hardware, to your real electronic control unit. So that's a typical development process for an embedded system. You might have a little bit different development process, but I guess you understand where I'm going with this. So most embedded projects are not tested in early phases. And also they do not have tests for robustness. Robustness is a precondition for safety critical system, robustness tests. So where do we test usually? Usually we have some unit tests for the pure software components, as I mentioned before, maybe not for all software components, like asynchronous concurrent components are harder to test with unit tests. And in the end, you might have a big HIL system test, hardware in the loop system test for your complete ECU, or even a big system test that's something usually you do once, twice, or 3 times over the development process. So a typical time is there every couple of months or something like this, because it's very expensive and very late in the process also. So what we do is now we focus with the miniHIL on the rest, so on the white spots here on the landscape. So the miniHIL is able to test on an evaluation board, usually can also be attached to ECU maybe, but the usual use case is to run it on an evaluation board. So you have the evaluation board with the real target microcontroller or with several microcontrollers or several chips, and you only test on signal level. So 3.3 or 5 volts, for example, or 2 volt, whatever it is. This has the big advantage. You can test your complete software system, including all the drivers and including the hardware periphery on your chip. So for example, a PWM, you can measure this and you can use it for your test case. So that's the basic idea for the miniHIL. By doing that, you get a very deep test very early in the process. And it can also be used in the later stages of the process, because before you run the system test, you need a system test usually. But before you run the system test, you can run the miniHIL test on every change in your software to make sure that you do detect most of the software problems before you even go into the system test. Makes things much cheaper. Now, why is it so hard to automate HIL tests for embedded system? An example would be a motor control system for an oil pump or a lubrication pump, something like this. That's a real world example, by the way. In this case, we needed to test the temperature shutdown or all the error shutdowns, but in this example, temperature shutdown for all boundary values for 300 relevant system states. And that's a lot, because you do not only have 300 relevant system states, but also all the temperature values and so on. And what they had before, they put their system under test. This was the complete system, including the hydraulic system, the motor, the pump, the ECU, and the microcontroller in a climate chamber. 2 meters high, I don't know, maybe 1.50 meter deep. And now you can imagine how long it takes to go from plus 40 degrees centigrade to minus 40 degrees centigrade. That takes a lot of time. 2 hours maybe, or an hour for such a system, costs a lot of energy, and it's very, very slow. So theoretically, it would have taken something like 30 days to test for all the states needed for those shutdown tests, system shutdown tests. And it's very hard to automate, because you have so much hardware in the loop that things might fail at any time. For example, in a hydraulic system, the oil gets frozen or whatever it is, and suddenly you cannot run your test case. You don't care in your test case whether the oil is frozen, because that's in this case not a test case. You just want to test the temperature shutdown, but you cannot run your test because something else fails. Or the motor gets stuck, or you run out of fluid in your hydraulic system, so you have to open the chamber, the climate chamber, and refill the system. So that's all things you do not want to test. You just want to test your software logic on every change. And it's impossible, because you need 30 days for that. So actually it never ran really automatically for longer than a couple of hours. So what we did is we said, okay, now let's focus on the microcontroller with the complete software stack to help the developers to make their software extremely robust. And by doing that, we simulated the complete environment, all the power electronics, the sensors, the actuators, the motor, and so on. It's not as hard to do as you might think. And suddenly we've been down to 50 minutes of test for all the tests, not only the temperature shutdown. So actually after every software change, you can run this test fully automated. And because it's also easy to automate, your hardware cannot fail because it's completely simulated. You might have bugs in the simulation, but that's something you fix once. And suddenly you have a very, very fast test system for safety critical software on your system. So that's the basic idea. Now, what can you do with a hardware-software integration test? The main goal is not to test single software components like the motor control or the temperature sensor or whatever it is, but the integration of those components into the software system, including all the drivers and electric signals. By simulating all those signals on the outside, you can put your system into almost any state you want to test it by changing the simulation. For example, for failure injection, you can run good world scenarios, so the happy path, but you can also run all the unhappy paths. You can break a motor, not by breaking a motor, but by changing the simulation. It just gives you a wrong signal, something like that. That's if you have the simulation, it's easy to do. And this enables a complete automation, speed, and depth in your test process. Let me give you an example. Again, the microcontroller is a black box in our test setup here, or more than one microcontrollers are also possible. The important thing is on signal level. So we provide signals, measure and provide signals for PWM, the digital inputs, outputs, ADC, and so on. And now I want to test my temperature shutdown paths. Now let's have a look at how we do this. So first step is we inject a temperature, for example, minus 41 degrees centigrade, by providing an analog value with a DAC, with a DAC. We provide the analog value for an analog temperature sensor. We know it's supposed to be 41 degrees now. And now inside your software is a black box in this case, the events are cascading through your software. In a black box test case, we do not care about how it does it. We only want to monitor what happens afterwards. So now what we need to make sure is, first, the PWM needs to be off after 100 microseconds. So for that, we have a PWM monitor that monitors that after 100 microseconds, so we trigger the neuron temperature, and after 100 microseconds, the PWM needs to be off for a certain time, for a second, for example, or something like that. Whatever your requirement is there. Now that's easy to do them if you have the IOs. And the other constraint here, or the other requirement or expected value, is that we get a correct CAN message from our application. That's a much higher level thing to monitor, because the lubrication pump, for example, of the system is attached to a crane. And a crane needs lubrication to work. And if the lubrication does not work and the crane continues to work without lubrication, it might break. And imagine what happens if a crane breaks. If, I don't know, whatever happens when a crane breaks, it might, or this is very, very safety critical. So that's one example for what you can do with this kind of hardware-software integration test. So it's highly system relevant. Now, what are the advantages for safety testing on microcontroller level? You can test your software system as close to reality as possible. You can test the complete unmodified software with the target compiler on the real microcontroller, including all the drivers. That's a very, very good test depth. It's for many projects it might be the most important test for safety. Yeah, on a system level, you cannot modify your environment necessary to test all the shutdown paths for errors, for example. We have many customers that test all the error shutdowns on this level, because they cannot do it on system level, and they cannot do it on unit test level, because, yeah, they have no idea what the driver might do in your test case. The tests include the drivers. You can run also a code coverage during the integration tests. That's possible. It's a bit more work than for unit tests. There are hardware solutions for that. There's software solutions for that. And by doing that, you already can see what's your coverage to spot gaps in your test strategy. It's not to verify that your test cases work. So it's not a quality proof of your system or your test cases, but it's a metric that gives you the gaps in your test strategy. Very important to do this from a certain safety level. Most complex problems can be found on this level, because the most complex problems are usually, because it's so big, in the software. Yeah? There are systems where the complex problems are located elsewhere, but most complex problems nowadays result of software problems. You have a very good test automation with continuous integration, because you simulate all the environment, and you only need the wires to hook it up to your system on a signal level. So in system or CU level tests, many errors cannot be tested without destroying or modifying hardware. You can test most error paths on black box level by fault injection in the environment simulation. That's what we do here. So now, if you need to test for security or for safety critical systems, you might need to prove that your test system is working well. There are different strategies to qualify a software for safety critical system, but one strategy is to certify or qualify your test tools, and we have a little support for that. So you need a certain tool confidence level. This depends highly on the domain, railway, automotive, avionics. The test tools need lower level than the development tools, so it's not as hard to do as for development tools, but it's a certain effort. You could also certify the complete test tool chain. That's extremely expensive, and it needs to be done for every new version. So that's usually a very expensive way that's not done. It's prohibitive in many cases. And you also can do a tool qualification, so a project-specific tool qualification, and this can be standardized by a high degree. And you also could argue proven in use, but that's an argumentation for complex systems, test systems. It doesn't always work, and it's not always, it's not always okay. Many projects might argue that way, and it might be okay, but not in every case. So the way that we take is usually the tool qualification way with our customers if they need a tool qualification of some sort, and we have a tool qualification kit for that. Usually you get away with 70-80% standardized tests from our side. You get a full report on all your tests, also on your own tests. But for example, if you have a very specific, SPI protocol or certain interfaces that are not really standardized, then we cannot provide a standardized test for that. But you can add to our standard qualification kit, you can add your own tests to fill the gaps. And of course, we help you to do that. That's a very fast way in comparison to do 100% on your own. Now, by doing that, you can speed up the tool qualification with our process templates and tests and reporting. Usually, you always need to adapt this to your process a little bit. Now, how do we do all this? So our motto is keep it as simple as possible. So we start with a very simple hardware platform. On the right side, you see the system under test. That's a microcontroller you want to test. It runs, for example, in many, so it's STM32 in this case, Cortex M4. It runs, for example, in one of the system of our customers. Kercher is testing the complete product lines for the home line and for the professional line with the miniHIL, because they can switch between different product members of the product line or variants easily by just changing the software setup and the wiring, also automatically. Now we hook up all those pins of the microcontroller over this patch panel here, over the wire jumpers. We connect it with our test system. That's also a microcontroller because it needs to be fast, it needs to be deterministic, and we simulate the complete environment, so the motors, the bus protocols, the sensors, and so on. And we also run the test cases on this environment. So now we need drivers for those signals in the test environment. We need the environment simulation, and we need the test cases. Those are the three things we need here on this side. Now, how do we do this? Because it's relatively complex to build this. We have a model-based environment. You can build simulation and test models, so structure and behavior for simulation and tests, including all the IOs. On the model base here, we generate C code we compile, we flash the C code to our test system, and then we run in real time, a real hardware, real-time system. We run the environment simulation in the test cases. For example, for a motor simulation, you need 30 kilohertz, for example, for a typical motor simulation to simulate it, and it needs to be hard real time. So you could not do this with Python, or you could not do this on a personal computer, on your desktop or your laptop, because it's hard real time. Yeah, so that's why we run also the test cases in C, because we can react in 100 microseconds or 10 microseconds in a test case on some signals or so. That's a really fast system. Now, then while we are testing, we're logging the reports, and we creating visual reports, diagrams, and so on to analyze and test what happened in your test system. And to learn and iterate, because as human beings, we understand those diagrams better than a text log or whatever. Yeah? Debugging is also not a good idea in a concurrent asynchronous embedded system. If you hit a breakpoint, for example, your system doesn't work anymore, so you get a failure for sure. So that's why we use a lot of logging, also low-level logging, like sequence diagrams for every call in our test system, for example, for every value and so on. So now we learn and iterate. If you have a bigger project setup, for example, if you have many developers, you might not want to run the miniHIL on your desktop, but distribute it in a distributed development environment. You want a continuous integration server. So what we do here is, if you have more than one developer or several developers or even bigger teams, or if you have a distributed team worldwide or more than one project, many projects, you might want to have a continuous integration setup. In this case, we have, for example, 8 miniHILs in a continuous integration rack, in a 19-inch rack, 1.20 meter high. And on every commit of every developer, wherever he works, the miniHIL hardware and the loop tests are run. Usually within a couple of minutes or so, you get a feedback whether your test ran or not. So you can attach this to a pull request in your GitHub, GitLab, or whatever it is. So it's easy to do, because everything we're doing is also always able to run on command line. So we want to test every code change for every developer within minutes. And for the longer running robustness tests, for example, we could run them in a second stage. So on a commit stage, you get an answer after 5 minutes. And then every couple of hours, you start the second stage, the capability stage, to run your robustness tests, iterative tests, or combinatorial tests, which is also possible with the miniHIL. So combinatorial tests, we have a very nice method to generate them. You define on a very high level of abstraction all the possible paths through your system. This regards different data combinations, different shutdown paths, different parameter paths, or also behavior through your system. You have a very good so-called state transition test method to define this. And then we generate all the necessary test cases needed to cover this graph with all the test cases. So for example, here you can see all passes from initial to end are here generated as distinct test cases. Here you see the states, and here you see the test snippets you're activating while running those test cases. And you can imagine, if you make the graph a little bit bigger or the metric a little bit higher, you might generate, I don't know, 100,000 tests, 1 million tests, whatever it is, you need to cover your problem space. And usually it's very fast because it's all simulated. So you have a formal description for the black box behavior of the system. Out of this formal description, we generate all the paths and data combinations. It's redundant. That's important, because this is not the state machine in your system, but a separate state machine defined by the test developer. for the expected values, expected behavior. And it's proposed by some standards for safety critical systems also. That's a very good deep test method. Now, I make a little demo for a typical motor control application. It has a STM32, generates 3 PWMs, block commuted with block commutation, and the motor generates 3 Hall signals as digital signals. Here we have the motor simulation, here we have the motor controller. We have 1 analog signal for the temperature, and we have a UART, could also be a CAN bus, LIN bus, whatever it is, to control the speed of the motor controller, to get error messages and so on. So it's a simple but real-world system. And a typical test execution looks like that. On an electrical level, we just use the Celea and logic analyzer, so nothing special here, to log the test execution. You don't need this for the test automation, but it makes it easier to understand what our system does. For example, we measure those 3 PWMs in our system under test, then we generate the Hall signals as a real motor would do. And here we satisfy the UART interface. We send commands to our system under test. And we also have an analog value here. That's the analog value for our temperature sensor. So here you see, by the way, the equivalency classes of the temperature sensor and the boundary values. So for example, temperature too high, temperature too low, temperature almost too high, almost too low, and so on. And by doing that, so those are again those same signals, PWM and the Hall signals. You see it's a closed loop simulation here, PWM in, Hall out. And now we can run test cases like we change the speed in our system under test. The system under test makes the PWM frequencies lower. So here, and the simulation follows by making running the motor slower and generating slower Hall signals. Then another scenario is temperature shutdown. So on a temperature shutdown, we want to see exactly that the PWMs are, after, I don't know, 100 microseconds, going to 0, all of them, for a certain time. You see it's a closed loop simulation because the motor slows down. So it has inertia, so it slows down. It's a real simulation. And then we recover, we have a warning temperature, the motor gets a little bit slower, the motor recovers, and so on and so on. And you can do this for all the sensors, for all the situations in your system. Now, let's make a very small demo, just that you get a feeling of what we do here. So I have my development environment. It's model-based, as I said before, and I have on my desktop here, I have my miniHIL set up. As you can see, it's smaller than a piece of paper. That's actually here a size of a piece of paper, A4 paper. And that's my system under test. Those are the PWMs and so on, and the Hall signals I mentioned before. So it's exactly the example I give you now, and that's our test system. And all those IOs here are attached to the test system. Those IOs here, or those pins, are attached to my system under test. So I can rewire it at any time. So now let's have a look at the implementation of the simulation and the test cases. Down here, we have all the adapters, the standard adapters, but also specialized adapters you might need for your test environment. You can implement, for example, protocols as state machines. That's a real state machine generator. It's a full programming language for state machines. You also can combine different blocks in your simulation to new functionality. Here we have a motor simulation. In this case, that's a state machine. You could also integrate a MATLAB Simulink block to simulate your environment here. So IOs, simulation environment, motor temperature, motor simulation, closed loop, open loop. And here I have my test cases. And instead of a state machine, I describe my test cases as a specialized language, test language. Again, it's a model-based language, textual language, and you can use this to define your test cases. So for example, here we have all our test cases. Let's dig into one test step here. We can send a new speed, for example, to our, here we send a new speed to our system under test, and we actually expect that the reply tells me, okay, I received this. And I can also check the speed of my target by asking my motor simulation, hey, is the target really controlling my motor correctly by delivering a speed between low and high? So that's how we do it. Then we go one step up, and we create test sequences and test suites. And as you can see on the right side, we always generate the expected scenario directly as a graph, as a state machine, as a sequence diagram with all the parameters. So now I generate the test cases and the environment simulation, and I run it on my system under test. So that's a little graphical user interface I use to run my test cases. Those are actually really the motor demo integration tests, for example. That's exactly what you see here. And now I can run my test cases. And here on the left side, I'm going to pulling a plug while the system is running, the test system is running, to emulate a problem in my software. So now I run the system under the test system. And while it's running, I just pull the plug here. Now I deactivated the UART, RX or TX. I reconnected. Now you see here the combinatorial tests. So they make a much deeper proof of what might happen. And here you can see now which test cases failed. And here you can see actually what happened while this test case failed. For example, here, this test case, test limit temperature, failed by running into a timeout because it did not receive the UART command back. So I click on the error, and in my system under test, I get exactly the location where the error occurred, isolated in the step. So I was waiting for this UART control active, and I did not receive it. So that was the problem here. And if you want to know the context, that's not enough. You go back to a log, and you see the complete history of everything that has been done in this test case or test suite or test step. So by doing that, you have all the information you could possibly get to find out what your problem is. And when I fix the problem, when I make a bug fix, I reconnected it again, I just could run the needed test cases. So I deactivate everything. So for example, and just run the test cases I need. In this case, it runs much faster. And now I know again that my system works, everything's green. And if I really want to know that everything works, for example, on the continuous integration server, I would suggest to always run all the tests. If they take too long, make 2 stages. And that's it. And by the way, that's also a very good thing for me. If I run demos like this one here, I always know that my demo works because my demo is the test case. That is really, really valuable for presentations as well. Okay, so that's it so far. I hope you enjoyed this little webinar, and we have many more webinars coming up with Eclipseina in the next months. And hope you enjoyed the webinar, and goodbye. Thank you, Annette, for the possibility to be here, for the ability to be here.
Yeah, so I don't know if I'm back already in the picture. I have some questions in the chat, Thomas.
Yeah, sure.
You're not done yet.
Okay, good.
One question is, what are the signals that I should focus to make my analysis? I think it would be best if you explained now the practical part in your demo example. Maybe you can answer the questions with type of signals, which you have to focus on.
Yeah, so first of all, you need to satisfy the interfaces that are needed to run your system. So for example, in your system, let's take this example again. Let's here, for example, if that's your system, I know it's a simple system, but smaller microcontroller systems might have, I don't know, 10, 20, 30 signals. Bigger systems might have 150, 200 signals. And for example, if you have this setup and if you leave away the whole signals, you cannot simulate the closed loop simulation. So your system under test will immediately detect that it doesn't work. So if you cannot, if you leave away things that are necessary to work in your system, you do not even get to the state where your system can actually be tested because you fail immediately. So for this system, you need at least for the motor control those signals. Maybe you can, if you do not want to make a temperature test, you at least need to provide an analog value that's okay for your system under test. It can be a fixed value if you do not want to run temperature tests, but you need to satisfy this interface because you do not want to stop out the functionality in your system under test because you want to test your system as it is and not deactivating functionalities. Also the UART. Sometimes there is functionality you can leave out if you do not need it in your scenarios. That's okay. Then leave it away. But usually it's easier to simulate the environment with our predefined simulations and so on than you might think. So in this case, to detect a problem in your, for example, that your motor controller does not shut down after a temperature sensor, let's say error, after 100 microseconds, you really need those signals. But you might not need the, I don't know, for a certain other scenario, if you do not want to test this, you might get away with not providing a pressure signal or a CAN bus. So for example, if you have a CAN bus, a LIN bus, and a UART attached to this ECU, and you only use in this variant, for example, for your microcontroller system, you only use the UART, then you only need to use the UART here for testing. I hope this answers the question a little bit. But yeah, you do not get away with just simulating the 3 signals you want to test because your system actually needs to work. I hope this answers the question a little bit. Okay. Next question.
There are more questions. Yeah, so we have one person who put several questions. The first 2 I would answer, and another one is a technical one I give to you. One question is, how can I access the presentation? We will continue to provide this live event like the other live events on YouTube. So it will be still available to watch it. The presentation as it is, the PowerPoint or PDF, will not be provided. But you can rewind and get all the explanation, again, looking into details on YouTube. This was one of the question. And the other question was, where can I order the miniHIL? I think that we provided the link to Protos software in our description of this live event. So you can either see the one slide which Thomas presented, or in the easier way to just go into the description and you will find all the information on Protos there. Mm-hmm. And the third question is, or it's more like a request, could you please explain the tools of HIL like PXI and DSpace tools, like the connection to these kind of tools?
Yeah, certainly. First, please just send me an email or contact us over our website, but you feel free to contact me directly at this email address I'm providing here. If you have any further questions, we can make a little call and we can answer everything, and we can talk about your test requirements and see whether this method makes sense for you or not. That's very important. I don't want to sell you anything that doesn't make sense for you. So please let's talk about this in detail. Okay, so what's the difference basically to the bigger test systems like a DSpace or a Vector or PXI or whatever you mentioned before? The big difference is that we focus exclusively, usually, on the signal level tests on the microcontroller level. So if you have, for example, a DSpace or a Vector systems, all good systems, please don't take me wrong here, but they have a hard time to test on a microcontroller level. You can do this, but you have the hardware is really big, really expensive, and it's much slower than our system for this use case because we optimized our system exactly for that. And this also gives you an idea about the pricing. So a miniHIL might be or is definitely much more cost effective than a DSpace system because the use case is a different one. So usually we do not run the big system test with 400 volt motors or whatever it is, but the microcontroller test to prove the functionality on a software level. So that's the difference. And also for systems like DSpace, usually you need an additional license for MATLAB Simulink and other software because you need some kind of environment simulation. You can also use Simulink to integrate it into our test system, but you do not need Simulink or MATLAB Simulink to run our test system. In most cases, you get completely away without additional software there. And so, of course, our software also costs something, but you do not necessarily need Simulink or something like that for that. Yeah, I hope this answered the question. So the main difference is that the focus of something like DSpace and Vector and so is more on an ECU level or on a system level, and our level is really the signal level of a microcontroller or several microcontrollers. So the logical level, if you will. Yeah. Okay. Any further questions?
Okay, Thomas, do we still have time for further question? There's I think we skipped one. I would go as they came in. It's if the system under test is not real time or not time critical, can the test system simulation run on the PC? I would, from my point of view, to say this, even extend the questions and say, yeah, if it's real time, you can still, I think, test on the PC. And what are the constraints to test on the PC if it's real time?
Mm-hmm. Well, if it's hard real time, it doesn't make sense to, depending on the speed, of course, it doesn't make sense to run it on a PC. But we have customers that actually run the test cases completely on a PC. If it's not real time or soft real time, you can even run it on Windows. So the generated code then runs on Windows or on Linux RT. So with Windows, you get away with something like 50 hertz, more or less real time. So if it's slow system like let's say a chemical system, for example, you could get away with that. We actually have customers that do this. For real-time systems that are not so fast, with a millisecond or maybe 5 kilohertz or something like that, you could use a Linux RT system. Yeah. And for harder real-time, very faster systems, up to 30, 40, 50, 100 kilohertz, you can use the miniHIL hardware platform. Also for things like SPI, I2C, usually you need real-time. And if it gets faster, we have an addition FPGA add-on. You just plug it into the miniHIL, and here you can get up to 50 megahertz with your simulations and interfaces and so on. So it scales extremely well. The biggest use case is usually a standard miniHIL setup, as I've shown you, with a microcontroller. And also, if you have, for example, we have one customer, they have a very big CAN bus systems with thousands of IOs over CAN bus, and we simulate 8/8 CAN buses, the complete hardware system on a PC. But it's not hard real time. It's 50 or 100 hertz or so, and this can be done easily on a PC with Linux RT up to kilohertz. But then you need different I/O connectors. For example, we have adapters for various CAN or LIN bus products out there. You might know them, and you can use basically the miniHIL software as I've shown you, but on the PC. Yeah, hope this answers the question.
Okay, and then we have the next question, which was on the screen before, from Mohammed Hilal. Yeah, is the miniHIL applicable with TI boards like C2000 series or like TMS 32F 280 0392 evaluation boards?
Yes, it is, and no, it isn't. I show you what we have there. Again, we developed initially the miniHIL for STM32 microcontrollers. That's why almost all the STM32 microcontroller boards, evaluation boards, directly fit on the miniHIL. 3.3 volt and STM32. Then if there's an evaluation board, it usually fits directly on the miniHIL. But we have many other customers, so STM32 is about maybe not even a third of our customers. And for the other customers or for the other microcontrollers, usually we develop a little evaluation board like this that fits directly on the miniHIL, or we have an adapter that also is, for example, for 5 volt boards, not only for 3.3. And then you get a little bit different setup. And of course, we or you have to develop this hardware adapter. That's usually not so costly, but at some point we need to adapt the signals to the miniHIL board. But you could also, for example, if it's 3.3 volt or 5 volt, you could also connect the wires directly. You could place, for example, if you have an evaluation board, you could place it next to the miniHIL. So here on the side, just put it on the side and wire it directly without those adapters. That's usually a very fast approach to get a first test set up. And then when you have your test run up and running, you have enough time to develop a little adapter that makes the tests mechanically and electrically more stable. Let's say up to 20-30 kilohertz. Usually such an open wiring is not a problem. If it's something you would do with an FPGA, maybe you need a little bit different. You need an adapter here. So it depends on the signal quality you need to test your system. But up to 20-30 kilohertz, usually that's the signal quality is good enough to get away in the first step without an adapter. So I hope this answered the questions.
Okay, do we have time for a very last one?
Well, I have enough time.
Yeah, there is the question on the field where it's applied in. Is it possible to know what field you are working on? And maybe working on meaning including your customers, in which areas the miniHIL is applied?
Yeah, I can give you some examples. So yeah, let's take those two. No, those are not. That's not the one I'm looking for. Yeah, that's the one I'm looking for. Sorry, I need to. Yep. Okay. So basically, we have customers in all fields of industry. So basically, all the domains you can imagine, and it's also pretty much distributed over all the industries. So there is no specific focus on automotive, as you might think in Germany. So we might have I don't know, 20-30% automotive customers, but all the rest is completely distributed over housing infrastructure, pumps, for example, for water, medical fields, laser equipment, or for surgery and things like that, cleaning equipment here, railway systems, avionics, airbags for motorbikes, for cars, and so on and so on. And I give you 4 examples for reference customers. Rheinmetall Automotive, that's a typical automotive component customer. So they do all kinds of components for cars. So pumps, climate compressors, exhaust valves, and so on. Then Dainese, motorbike clothing. They have airbags in their motorbike jackets and in their motorbike suits for racing. So there we test the complete trigger of the airbags. That's of course everything safety critical. Then we have Freudenberg. They have really big systems. So the system is 10 meter wide and 2 meters high. It's fuel cells for trucks and ships, and they have thousands of IOs. So obviously they cannot test this directly with the miniHIL hardware, but we're running this because it's fuel cells are relatively slow. We run this test system on a PC with real-time Linux or so, and have many CAN adapters to test all the IOs. So we are talking about a couple of thousand IOs there. And Kercher, they test all their product lines for their professional and home lines, or almost their complete product lines, 20, 30, 40 different products with several miniHIL boards and several miniHIL workspaces. So you do not need, for every product of your product line, do not need a new miniHIL. Usually you get away with less miniHIL boards than you have products because the environment is simulated. Yeah, so those are typical customers we have for the miniHIL. If you have any further questions, please don't hesitate to contact me. Yeah. Okay.
So thank you very much, Thomas, for all your explanation. And it seems like the interest has been very, very big because we had all these questions this time and needed some extra time to finish. The question was to please share the email so that you can be reached. As I said, it's in this stream link. We have it in the footer, and it's also in the slides which have been in the stream presented. For the next events, together with Thomas, it will be also again on the Eclipseina channel, but they of course also have own events. We will, in addition, publish again an event at Eclipseina channel on LinkedIn where you can sign in. So I hope it's easy to find us. And I would like to thank again everybody of you for joining us today and staying until the end, which is more than an hour. I wish you a very nice remaining day. Thank you and bye-bye.
Thank you. Bye.